So welcome everyone to today's seminar. We have Chris Kapulkin talking about invitation to discrete homotopy theory. Go ahead, Chris.
Great, thank you so much. Thanks for having me. It's a great pleasure for me to connect with this community. I think Nathan and Daniel, my two collaborators, should be here. If they are not, they will join shortly. I think we had some minor trouble getting the room for them, but yeah. So I should warn you, I was told to prepare for 40 minutes. So what I did is I took two 60-minute talks and stuck them together. So I might be going a little bit over time. But just tell me to shut up and I'm happy to comply. Okay. So to get us started, I'll say this talk has two parts. The first part is about homotopy. The second part is about homology. And the first one is more theoretical. The second one is more about the implementations. To get us started, I need to do something here. Did that do anything? No. Okay, I see. Okay, so to get us started, for part one, I'll mention my main references. So discrete homotopy theory, its origins in the form I'll be describing go back to the early 2000s and the work of Barcelo and her collaborators, but the ideas can be traced back to the work of Atkin, who was a physicist at Oxford back in the day. And in the 1970s, he published some papers about certain homotopy theory of simplicial complexes. He wrote a famous book, Mathematical Structure in Human Affairs, where he argued that this can be applied to pretty much anything, including chess positions, pandemic management, and so on. And then the last two papers are kind of my recent contributions to this. So one paper of Daniel Carranza and one paper of Oded Mavin. Okay, so if we're going to talk about homotopy theory of graphs, which is what discrete homotopy theory is supposed to be, we first need to talk about graphs. So for me, a graph will be just a set with a symmetric and reflexive relation. And the way I would depict such a graph is this. So the elements of the set X are the nodes, and then the edges indicate the relation. Now, I said here that the relation is reflexive, meaning every vertex has a small loop on it. It's so small that you can see it, but if you squint it, you still won't be able to see it. It's so small, okay? So, but they are there, just believe me, we're not drawing them. Now, if I'm going to talk about homotopy theory, one thing I know is that it's not the spaces that are important, it's the maps that are important. It's the maps that can be homotopic. So a graph map will be the only reasonable thing I can say in this situation, namely a graph map will be a function between these sets preserving the relation. Okay, so in this picture, my graph maps are allowed to contract edges to a vertex, but if there is an edge between them, then in the source, then there has to be an edge in the target. So here are some of my favorite graphs. So one of them is kind of a line, IM, that goes from 0 to n. So it has n edges. In particular, maybe I'll mention that I0 itself is just a single vertex with a loop on it, and I1 is just a single edge. Then there's an infinite line, so integers with an edge connecting two consecutive ones. And then I have cycles. That's my kind of favorite graph for all kinds of examples. So it's n numbers arranged in this cycle, and two particular examples are C4 and C5 that I think about a lot and will be important in this talk. Okay, so now let's think about the graph maps. So one thing that you might notice is that for any graph X, like the graph over here, there's a unique map to I0. So I0 is this graph with a unique vertex. So I just send all vertices to this unique vertex. And since there's a loop on every vertex, I can do that. There's no problem with edges. On the other hand, maps from I0, the single vertex, to X correspond to just picking a vertex of X. So there should be 5 graph maps from I0 to the graph on the right here. Okay, so I'll give you maybe 15 seconds to think about that. So how many graph maps are there from I1 to C4? So single edge to a 4 cycle. You don't have to answer. If you want to, you can unmute yourself and say something. So I'll give you just one more second, just so that you can think it through. Okay, so the first thing you probably thought of is 4. There are 4 edges in C4, so there should be 4 maps. But remember that every edge can be, I can pick an edge this way or that way. So there's actually 4 more, but actually I can contract edges to points, so there should be 12. So if you got 12, congratulations. No one ever gets 12 at first. Okay, next. If you're really bored at this point, I succeeded in making you bored in less than 5 minutes. Figure out how many graph maps there are from C4 to C5. There's a lot. So good luck and have fun. Okay, so next I want to tell you how to build new graphs from old graphs. And the operation I'm interested in is the box product, and the notation will become clear. So sometimes it's called the Cartesian product in graph theory, which is very sad. Okay, so what is this box product? So I take 2 graphs, and as the set of vertices, I just take the product, the usual product of sets of vertices, and then I'm going to join 2 pairs with an edge if the first coordinates are equal and the second coordinates are related by an edge, or the first coordinates are related by an edge and second coordinates are equal. So for instance, if I try to box I1 with I1, I'll get C4. And the horizontal edges here come from the first condition. So they have, on the top, they have 0 and 0 on, so the first coordinates are equal, and the bottom 1 and 1, the first coordinates are equal, and then vertical edges come from the second coordinates being equal and the first coordinates being related. The point here is that there are no diagonals. That's an important part of this theory. Okay, so now that I have that, I can actually talk about homotopy theory. So I can tell you what a homotopy is between 2 graph maps. So if I have 2 graph maps F and G, a homotopy between them will be a graph map from X, this box product IN for some n, to Y. And this map will restrict to F on the 0 end of the box and on to G of X, or to G on the n end of the box. Okay, so really what I did is I took the usual definition of homotopy from topology, I replaced the product with the box product, and I replaced the unit interval with IN. And that's all I did. But that automatically gives me the notion of a homotopy equivalence. So when are 2 graph maps homotopy equivalent? Well, if there's a homotopy equivalence, that is a map for which there's a map backwards, such that the 2 composites are homotopic to the respective identities. Okay, so that's a notion. Can I prove it? So one thing that we prove probably when we teach algebraic topology as a first example is that the unit interval itself is contractible. That is to say that the map from the unit to the point can be is a homotopy equivalence. So this is true in this theory. And how is it proven? First, as my homotopy inverse, so a map in the opposite direction, I'm going to take a map that picks out 0. And now I have to give you 2 homotopies. One is a map between 2 maps from I0 to I0, but there's only one such map, so I'm good. This homotopy is clear. The other one is a homotopy from between 2 maps from IN to IN. One of them is constant 0. The other one is the identity. And this non-obvious at first homotopy is given by minimum. If I take the minimum of IN between IN and IN, I get a well-defined map, graph map, on the box product, and it assembles into this box n by n, where first I have a row of zeros, then 0, 1, 1, 1, 1, 1, then 0, 1, 2, 2, 2, 2, 2, and so on. And on the bottom row, I'm going to see 0, 1, 2, n. Okay, so the interval is contractible. But what would not be contractible in this theory? So it turns out the map from I infinity to I0 is not a homotopy. So that's a first departure that we see from the kind of continuous theory. So the real line in usual algebraic topology is contractible, right? Because the further you are, you can keep going faster and faster. Here we don't have it. We kind of need to move step by step. Like it's discrete setting. So this thing is not contractible. How can we see that? Well, suppose there was a homotopy inverse. Since I can just pick any point, because in Z everything looks equally good, I may take 0 to be this homotopy inverse. And so suppose that I have a homotopy from I infinity box sum I n to I infinity. Well, this homotopy would in particular mean that I can find a path from 0 to n plus 1 of length n, because right, on this box I infinity to I n, right, I should see zeros on one end and identity on the other end, and then everything should be connected by a path length n, and that's just impossible. So this discreteness means that I infinity won't be contracted. If you're looking for further departures from classical theory, here is one. The map from C3 to I0, so the 3 cycle, is a homotopy equivalent. So for the homotopy inverse, because I'm really boring and I always pick 0, I pick 0. And now I'm going to give you the homotopy. So the homotopy is given by this. What this represents here is C3 box I1, right? And on one end of it, on this kind of back end, I see just zeros. And on the front end, I see 0, 1, 2, so the identity. So I just gave you a homotopy from C3, or a map from C3 box I1 to C3 that shows that C3 is homotopic to is homotopy equivalent to I0. In fact, you can replace C3 by a discrete graph. Going further, the map from C4 to I0 is also a homotopy equivalence. And again, the homotopy inverse is given by picking out 0. Now, I need to work a little harder for the homotopy. Namely, I need to do it in 2 steps. I'm going to give you a map from C4 box I2 to C4. So you can see that on the back end of this kind of double cube, I see a bunch of zeros. And then on the front end, I see 0, 1, 2, 3. Now, you could try to do it as I did for C3 in 1 step, but then you would have to have an edge from 0 to 2. You don't have that edge in C4. So you're forced into this 2-step process where you kind of take the square and smash it one way, and then you smash it the other way. That's the way to think about it. Okay, so C4 is still contracting. Now I'll give you maybe 10 seconds to think about this question. Like, is it true for all natural numbers? Is C5 also contractible? Is this map? So again, if you want to take a guess, feel free to unmute yourself. I always welcome guesses. But okay, the answer is, so the first thing, whenever I give this talk in person and I could actually do a show of hands, I get 50-50. And that's one thing that I love about this theory, that like, no matter what you did, no matter if you're a topologist, combinatorialist, and so on, like, it's just guessing. No one knows. So is this a homotopy equivalence? And as you might have inferred, not through any mathematical reasoning, but through sociological reasoning, if I'm posing it like that, it's probably because it's a trick question. So it is not a homotopy equivalence. And to do that, to understand why, we need to talk about the fundamental group of a graph. So if I have a pointed graph, so a graph where I distinguish a vertex, I'm going to define its fundamental group as a collection of maps from I infinity to x But these maps will send almost all points to x0. So it's really kind of active. There's an active area only on some small finite bit, and everywhere else is just x0. I could alternatively use just finite paths, but then I would have trouble doing the thing at the end, which is quotienting by homotopy. So I need to quotient by homotopy at some point to get a group so that things behave nicely. And if things have different domains, it's harder to say what does it mean to be homotopic. You would have to come up with some padding, and you might get something really weird looking. I'll mention that this fundamental group, so that goes back to the first paper I mentioned. What I want to bring to your attention here is that this is the work of Barcelo, and then pretty much 3 applied mathematicians. So Barcelo is an algebraic combinatorialist, but Kramer, for instance, as you can see from the affiliation, is in physical science laboratory, whereas Reinhard Laubenbacher now, although it says math here, he is currently in the Department of Medicine. So this definition comes from actually serious applied considerations. Okay, how does the group operation work? As I mentioned, there's only this finite active area, and what my group operation does, it concatenates these active areas. So it takes some active area from one thing, it takes an active area from other thing, and then it stacks them together. Now you can ask, oh, do we stack them here? Do we stack them there? It doesn't matter. We quotient up to homotopy, and this is then well defined as an operation on A1. Okay. This fundamental group is a homotopy invariant, meaning if 2 graphs are homotopy equivalent, then their A1s are isomorphic. In particular, it's easy to compute it for I0, the point, and therefore you get it immediately for C3 and C4, since we already showed that these are homotopy. Now, when you try to compute it for C5, you find out that A1 of C5 is actually Z. It's the integers. And the way you would prove it is you actually read Hatcher and pretty much go replace all on space to graph, and it all works out. Like the proofs are slightly different maybe, but not that much different. And so I infinity ends up being the universal cover of C5. Interestingly, the universal covers of C3 and C4 are themselves. So C3 and C4 respectively. In fact, using the same argument, you can show that the higher cycles also behave like the circle, or maybe a circle in this theory. And another thing that you can observe is that Cm and Cn are not homotopy equivalent. So they have the same fundamental group, but they don't have the same, they are not homotopy equivalent. And one way to see it is, well, one is larger, one is smaller. So any map from the smaller one to larger will omit some point in the larger cycle. And if you omit the point in the larger cycle, then the map needs to be null homotopic, because you can just contract every map into Cn that omits one point. So they are not homotopy equivalent, even though they have the same fundamental groups. You can also define higher homotopy groups. I'll go through that very quickly, but how does that work? Well, instead of taking maps from this infinite line, you now take maps from infinite dimensional, n-dimensional infinite grid. So it's this z to the n, if you will. And again, you're only doing something interesting on a finite bit of it. You can use Ekman-Hilton, moving these active areas around to get that these are abelian. And one thing you can show is that for all cycles, in fact, all higher homotopy groups are trivial, meaning these behave like the circle in homotopy theory. you can ask, okay, do these detect something? Well, they detect quite a lot, and they don't just see graphs as one-dimensional CW complexes. So in particular, for every n, there is a graph who's with non-trivial nth homotopy. Okay, I'll mention very briefly.
Before you go forward, can I ask a quick question?
Uh-huh.
So what breaks or nothing breaks if you allow the definition of homotopy also to be the box product with I infinity?
Then it's very hard to say what the endpoints would be. Does that make sense? Right, like if
yeah, I get it. Yeah.
I infinity doesn't have the endpoint. Yeah, okay.
Okay, thanks.
Yeah, cool. Okay, so these behave like the circle. Okay, so moving on, I can talk about weak equivalences as a homotopy theorist. My first thinking is, okay, if I have homotopy groups, I want to talk about maps that induce isomorphism on all homotopy groups. So this is what I would call weak equivalences. So for instance, the map from I infinity to I0 is a weak equivalence, because if you have to factor through some finite part of I infinity, you will in fact be contractible. But we proved before that this is not a homotopy equivalence. Likewise, maps from Cn plus 1 to Cn are weak equivalences. Like if I just contract one edge to a vertex, this is a weak equivalence, but not a homotopy equivalence. So as homotopy theorists, one thing that we learned very early is that there's something called Whitehead's theorem, meaning if you have a map that's a weak equivalence, isomorphism on all homotopy groups, if this is an isomorphism on all homotopy groups, then it's going to be a homotopy equivalence. And that fails here quite miserably. Maybe even more to the point, like sometimes you can argue, well, but Whitehead only works between nice spaces. Well, these graphs are as nice as it gets, right? We're talking about cycles here. So yeah. Okay, so before I go further with the theory, I'll just mention a couple of applications of it to tell you why you should care. So this theory was developed independently by several authors. One of them is Stephen Murrer, who was at Waterloo, just an hour short drive from here. And he developed it to study matroids. So matroids are essentially sets with some idea of linear independence. And when you have a matroid, you can talk about its basis graph. So it's a graph whose vertices are bases and two bases are related by an edge if they differ by exactly one element. And you can ask, okay, which graphs arise as a basis graph of a matroid? And it turns out that this weird fundamental group that I just defined for you is exactly one of the three conditions that you need in order to express it. I'm not going to go into the details of the local condition, but if Daniel is on this call, he knows. So all questions should be directed to him. Eric Babson developed something related to study hyperplane arrangements. Reinhard Laubenbacher is leading now a group working on applying this to understanding gene regulatory networks, something I know absolutely nothing about, so I will not say anything, but I know that, yeah, there's an application there. Combinatorial time series analysis, that's, I think, the original application of Laubenbacher from the 1990s that led to the paper I referenced earlier. Social and technological networks, that was Atkin's original application that he had in mind before the theory was as precise as it, mathematically precise as it is now. And in joint work with Nathan Kershaw, we're now applying it to data analysis, and I'm going to let him handle all the questions on this topic. I'll mention one other result. So when you have some graph invariant, you can kind of in topological combinatorics, you might ask a question whether there is a space you can associate to a graph such that this invariant somehow is a topological invariant of a space. So here, the question is, to a graph, can I associate a space such that the homotopy groups are the homotopy groups of this space? And that was resolved in the positive. And Sx is the geometric realization of a certain cubical set. So I don't want to go into the definition of a cubical set, but just think of a space that's glued together from points, lines, squares, cubes, and so on. So just a nice geometric object like that. And the 0 cubes would be the vertices of X. 1 cubes will be almost maps from, or almost edges. These are exactly the maps from I1 to X. So we know that these are not exactly the edges. We did this exercise earlier. 2 cubes are maps from I1 squared, the box of I1 with itself, to X. And the n cubes are maps from I1 to the box power of n into X. So this is how you get a cubical set, and then you glue these together according to how the faces work out. Now, if you're still thinking how many maps there are from C4 to C5, there's a lot. And just think how huge this object would be, right? Like there would be hundreds of n simplices. Well, 3 simplices for sure, hundreds of 2 simplices perhaps when we apply it to C5, even the simplest graph. So this is not workable. However, it's a very convenient tool that allows us to formally transfer theorems between the continuous and discrete setting. So certain theorems are more amenable to that kind of treatment and others aren't. So the long exact sequence of a vibration of homotopy groups associated with vibration is something that we were able to get just by using our construction. Okay, so the quick conclusions are discrete homotopy groups. These capture important information about graphs and networks, right? Like they appear independently in a lot of contexts. Like a lot of people develop them independently. There are several other examples that I didn't even mention here. They resemble the continuous setting in some ways, like we can get the long exact sequence of a vibration, but in other ways they are different. For instance, the Whitehead theorem fails. As a result, and it comes perhaps from from the fact that we're taking maps from something infinite, there's no good algorithm for computing them, and the solution here would be to use homology groups. Okay, so yeah, I'm ready to move on to part 2, but maybe if there is a question or two, I can try to answer it now before I move to homology. I don't know if anyone. It was a lot. It was very fast. It's not gonna get better. If that offer, I just want to be honest. Okay, you can ask me anytime. Okay, so discrete homology groups were kind of developed shortly after. So the original paper is again Alain Barcelo and collaborators. It to me is quite amazing how much Alain did in the theory, and kind of the comparison between this homology and path homology of Gregorian and collaborators is in 2019 paper, and then Nathan Kershaw and I have a paper on how you compute this efficiently. So let me quickly go through the definition of singular homology. So first, the hypercube graph is essentially what we saw before. It's these graphs that we hum out of to get this cubical set before. So you just I'll write Qn for the n-fold box product of I1 with itself. Okay, that's what this thing looks like. And now a singular n cube in a graph X is just a map from this cube to X. And so, for instance, if I take my favorite graph from earlier and I take here is an example of a singular 2 cube in this graph. There's of course more. Now these are related by face maps. So if I have an n-1 cube, I have 2 n ways, I'm gonna guess, to include it into an n cube, and these are just the n faces. So when I have a square, it should have 4 faces, and they are obtained by inserting 0 or 1 in the ith coordinate for I between 1 and n. Okay. And I can take then face maps of singular cubes. So this is the singular cube from earlier, right, that picks out this square. And one of the face maps picks out this this edge, and so this edge would be the face of a singular cube. A cube is degenerate if the two faces, the minus and the plus face in the same direction I, are equal. So for instance, this cube is degenerate. There is another cube that's degenerate. I would have to swap A and B on across the x equal y diagonal here to get the other degenerate cube. And perhaps the most underwhelming definition of all, a cube is non-degenerate if it's not degenerate. One thing you might be tempted to say is a two cube, say, is degenerate if its image is one edge. For instance, this cube is non-degenerate. Its image is one edge, but it matters what order things are traversed. So it's really like here, if I take the two faces, it would be AB and BA, not AB. So again, we see that maps from I1 to something, there's more than we usually think. Okay, so once we have a graph and a ring R, we can define a chain complex by taking Cn to be the free R module on non-degenerate singular n cubes in X, and these assemble into a chain complex with the differential given by this thing. So I need to subtract the plus and minus faces, and then so again, if you're familiar with cubical sets, this is essentially how you take how you define the differential of a chain complex associated to a cubical set, a normalized chain complex, and you get this chain complex like so. And maybe as an exercise, if you're particularly bored, you can check that this is indeed a chain complex, but that's not bad. Okay, so the discrete homology of a graph will now be the homology of this chain complex, meaning the kernel of delta n quotiented by the image of delta n plus 1. One thing that is easy to check from the definition is that the dimension of H0 is really the number of connected components. And one other theorem that we were able to transfer using the theorem that Daniel Carranza and I proved that I told you about earlier is that there is a canonical map from AN to HN of coefficients in Z, and this map is an abelianization for n equal to 1 and for x connected, and it's an isomorphism for n greater than 1 if x is n minus 1 connected. So this is the usual Hurewicz theorem that we kind of get for free just proving this earlier theorem. And the two graphs here, the graph on top, C4, will have trivial homology because even though there is a cycle it's C4, cycle of length 4. It's in the name that it's a cycle. There is a 2 cube that fills in that cycle, therefore it's contractible. On the other hand, there's no 2 cube that fills in the 5 cycle. Okay, I'll give you a few more examples of interesting graphs with interesting homology. So for instance, there's the green sphere. This is one way of seeing it. It's an octagon with 2 extra points. Okay, the north and south is connected to all the even numbered things, and north is connected to all the odd numbered things. And this is kind of our smallest model for S2. So it has the correct homology up to dimension 3, and above that, we actually don't know what it is. Okay, so this is a way of doing S2 in this theory. We can also do the projective plane. So at every crossing here, there is a vertex it's not drawn, but it's there. And I do this quotient where on the boundary, I'm identifying 0 with 0, 1 with 1, 2 with 2. And that, if you remember your algebraic topology, should behave like the projective plane. And indeed, H1 of this is Z mod 2. And it has the correct homology up to dimension 3. Okay, a couple of more graphs that I'll use for testing is C5, where I add little triangles on top, and this is has the same homology as C5. In fact, it's homotopy equivalent. We'll discuss that in just a second. And T3, which is essentially the box product of 3 copies of C5. So it's a 3-dimensional torus. Again, we know is homology up to dimension 3, and above that it's unknown. Okay, so can we compute this group effectively? So that's the topic of a paper with Nathan that you can find here. Throughout, we work with a field F rather than a general ring, but just substitute Smith normal form for rank, and all the algorithms work. And we ran it on Digital Research Alliance of Canada, 1 node, 64 threads, just for consistency. Okay, so how would I compute this naively? Well, I would try to generate all maps from Qn to X, all set maps, so not thinking about preserving anything. I would check which of these are graph maps, then I would check which of those graph maps are degenerate. I would compute the differential for those, and then I would compute rank. So this is highly inefficient. Like if you're going to compute maps from Qn to X, there's going to be a ton of them. And indeed, this is what you find out. If you want to compute, say, the 4th homology group of C5, you very quickly realize that that will take more than 1 billion years. And that's a lot of years. I tend to think that I'm getting old, but I haven't lived even half of 1 billion years, right? So that's a lot to take in all at once. So H4 was considered essentially out of question, even though people had some good output. So one thing that I found interesting is that people usually find that, oh, it must be the rank computation that dominates. Well, so if you ask what's so bad, it's actually not the rank computation at all. The rank is immediate. What's taking a lot of time is the setup of the matrix, computing these maps. So how can we speed up this process? So how can we do it so that we generate maps quicker? And how can we do it so that it's easier to check for degeneracies? Okay, so this one brilliant observation that goes into it that I think originated with Daniel and Nathan, one way or another, is that these maps can be generated inductively. Namely, we can obtain an n-dimensional cube by gluing 2 lower dimensional cubes. So if I have 2 cubes, I can kind of just check 4 edges, like 2 squares. I can check 4 edges to see whether they match. And then I get a full cube out of that. So rather than generating all maps and then reducing, I can actually generate cubes through this inductive process. I call this process taking the join. So that speeds up things significantly, but then it also makes it identifying degeneracies much easier. Namely, if 2 cubes that I'm joining are both degenerate in direction I, then so will be their join. So I can store each cube together with a list of directions in which it is degenerate, and then I just remove cubes that are degenerate at all before computing the differential. Okay, sorry. Next thing is that I have an action of the hyperoctahedral group. So the semi-direct product of z mod 2 to the n with the n-symmetric group, where Sn acts on z mod 2 to the n by permuting the coordinates on Qn. So this is, this is what you get. So this is the usual symmetry that swaps B and C. And then, so this swaps the 2 directions, where I can, like, the directions for me are ordered. So this swaps the direction like X and Y. But I also can just do a reflection. And so the reflections would, for instance, do this. If I want to get from the second to third, I can do a reflection. What reflection do I do here? Along the horizontal axis, I guess. So this acts on Qn, and therefore I obtain an induced Cn Bn action on my chain on the nth group in the chain complex. And now I can take the quotient of the nth group by this action. So I'm going to quotient Cn of X by this subcomplex that's generated by F minus, I want to say the symmetry of F, symmetry sigma of F, but I need to keep track of the sign. So the sign here, like Bn has a canonical representation as permutation matrices, and I just take the determinant of that matrix. Okay, and the theorem of Curtis-Green, Folkmar-Welker, and Georg-Wille is that the quotient map from C to C prime is actually an isomorphism on Hn, provided that the characteristic of F does not divide n plus 1 factorial. Okay, so what can I get out of it? Well, whenever I have a cube, I can easily store it along with all of its symmetries. And it makes this matching process of pairing squares or pairing higher dimensional cubes much easier, because as soon as if I have one cube and I have all of its symmetries, then if I match one cube here with a cube in the other equivalence class, as soon as I find one match, I found n factorial matches, because the symmetry of this cube will match with the corresponding symmetry of that cube. So I first deal with a much smaller matrix because I quotient it by like n factorial or 2 to the n times n factorial, but also it's easier to find matching. And if you just look at the first homology group of the green sphere with coefficients in F5, it's computed 3,400 times faster. And for higher high-ends, you see even greater improvement. I'll mention one other trick that we can use. So Barcelo, Capraro, and White in their paper that introduced discrete homology is they proved that this is a homotopy invariant. And so the idea would be that before we even start doing anything, we want to replace our graphs with smaller graphs with certain subgraphs such that the inclusion is a homotopy equivalence. Then we just compute things with smaller subgraphs. And one class of graphs where this is important is if you have a vertex whose neighborhood, and neighborhood, remember, includes that vertex, is contained in a neighborhood of another neighbor. So for instance, remember the C5 star that we had? The C5 star adds these triangles on top of every vertex in the 5 cycle. Now, if you look at your favorite added vertex, its neighbors are only 2 things on the in C5, right? But for either of those neighbors, their neighborhoods contain both of these. Therefore, I can remove them. So that reduces C5 star to C5. Better yet, if I have any complete graph like K10, it gets reduced to the point because everything is connected to everything. So I can just keep removing things. So K10 is reduced to the point through this pre-processing process. And so once you put all these improvements in, what you're going to see is that all of a sudden, H4 of C5 is computable in less than 1 billion years. In fact, it's computable in 10 to the 5 is a bit over a week. And other things that were previously not computable become quite computable. Pretty much H2 of anything can be computed with ease. Here are the improvements in this algorithm over the naive algorithm. Yeah, you can see that the improvements are big, but maybe I'll let you think for 10 seconds about one question. So the improvements for H0 of C5 and the green sphere and the C5 star are negative, or not. I mean, it's like we compute them like 10 times slower or 2 times slower. So why is that? Well, we do a lot of pre-processing. So it was fast to start with, and now we have to do a bunch of pre-processing. But of course, these times are so small, this is the previous slide, that that you don't really see that. Okay. So conclusions of part 2. We have a new software for computing discrete homology, and this homology, pretty much all the applications of homology that I told you about in part 1 are still applications, right? So in fact, when Reinhard Laubenbacher is thinking about chain regulatory networks, he's thinking about homology. Now, here is one open problem that is very interesting to me. So H0 and H1 can actually be computed using certain two-dimensional cell complex, which I obtained by taking my graph X as one skeleton, and then I glue in a 2-cell into every 3 and 4 cycle. So this is yeah, like if I can write it as a simplicial complex or a cubical complex, I have very fast algorithms to compute things there, so I can really cut down the size of things. But is there a similar basic shape theorem for higher HNs? So can I somehow figure out what 3 cells I need to glue in that would be less than what the theorem that Daniel and I proved tells you that would allow me to do that? Because then I can use all the techniques of topological combinatorics to compute these homology groups. So this is something that would really, I think, advance this theory. This one big area that I think might be of interest to people here that I haven't talked about is actual applications to data analysis. So what is it exactly that these groups detect that could be used for data analysis? And for that, I would say you should just ask Nathan Kershaw, who I hope is on this call. But I think with that, I'm just going to thank you for your attention and apologize for going over time.
All right, thanks, Chris, for the great talk. So for questions, maybe we can give the famous Zoom applause. So just unmute yourself and we can clap together. So. All right. Do we have any questions? Just go ahead and shout out, unmute yourself.
I should say Nathan and Daniel are responsible for the question. Yeah, they are on the call, I think. So
yeah.
If there are no questions, I can ask for another clarification question. I don't think I really understood this part. Are you saying that all maps from Qn to your graph can be built as a join from lower dimensional cubes? Is that this iterative procedure?
Yes, exactly.
And then all joins of
sorry.
lower dimensional cubes whose dimension add up to n? Is that how it works, or?
Okay, so I think this is a slide. So yeah, so whenever I have an n-dimensional cube, what I can do is I can look at 2 faces, and then so every n cube is built out of 2 n-1 cubes by making sure that the corresponding vertices connect. Right? So if I have 2 squares and I check that they kind of pointwise connect, then if I can connect them, I'm going to get a cube. So yeah, every cube will arise in this procedure. And sorry, I think I missed the last part of your question.
Okay. So if I want to compute 5th homology, I have to have computed all the lower dimensions anyhow. Okay.
Yes.
Thanks.
Yeah.
I have a question.
I'll just say this is exactly where the basic shape theorem would help a lot, right? Like if I just knew that I need to, but it's very easy to say, oh, I just need that, and it's very hard to come up with what the actual basic shapes are. And I'm sorry, Jason, I interrupted. I'm sorry.
No, it's fine. I have a question. So you said you run this on 64 threads. Does this mean this thing parallelizes nicely?
Yes.
Or yeah, okay, kind of linearly. Like if you run it on 64 threads, is it 64 times faster, or not quite as fast as that?
Nathan, do you wanna say anything?
Yeah, is my audio good?
Yes. Yeah, I can hear you.
Okay. Yeah, it's 64 times faster essentially. We didn't parallelize the rank So that makes it like slightly less than 64 times. And I guess there are some things that are parallelized, but everything that is parallelized is just 64 times faster.
Oh, cool. Yeah, I guess the pre-processing, can you parallelize that, or is that not?
Kind of. That one's one that isn't, but it's also
Yeah,
that's almost instant. So you
fair enough.
can pre-process a graph that you can like never compute the homology of, and you can do it in under like 1 second. So
cool. Nice. That's really nice. Thanks.
Yeah, so yeah, like I think like these numbers maybe show how bad I know pre-processing is, right? Like for the smallest graphs, it just slows things a little bit, but they were already so small that there's nothing there. But other than that, it like yeah, if you look at like as soon as you look at H1, you immediately see the improvement. Yeah.
All right. Do we have any more questions from the audience? Maybe I could just clarify. So you already mentioned that H0 is connected components, but you have any indication what the higher homology groups are measuring in this case?
Right. So one intuition that I have is that they find large holes in your graph, right? So you can almost say that this is a homotopy theory for people with bad eyesight. Like C3, C4, these are small cycles. So you think, oh, that's a point, and then you get to C5, and oh, I see, now it's a circle. So that's maybe one piece of intuition. But of course, they see, and H2 would see something like, does that work? No. Sorry, let me try to go to the correct slide here. What is it? Just a sec. The green sphere, perfect. Yeah, so if we run the green sphere, this is our model for S2. And so that kind of doesn't have any one-dimensional holes, but you can kind of see maybe that there's a two-dimensional hole there. And so that's what it sees, right? And then the projective plane, like, yeah, how do we get Z mod 2 in there, right?
Right. Okay.
So, yeah. And one way you can prove this result on H1 RP2, like you can prove it for A1, for instance. So when you take two disks like that without any identifications, you glue them together, you get something that's you can use Van Kampen to show it's simply connected. Therefore, that's going to be the universal cover of RP2, and so the usual argument that RP2 has universal cover S2, therefore the fundamental group has to be Z mod 2 applies. It's kind of very pleasing for a topologist, right?
Yeah. Right. Yeah, we got a question in the chat. So, is there any other structure rather than graph we can use in discrete way?
Yeah. So the original application. So the paper by Barcelo, Kramer, Laubenbacher, and Weaver worked with simplicial complexes, and essentially what they do is from a simplicial complex they don't phrase it this way, but they realize later, I think, that from a simplicial complex you can construct a graph, and then what they constructed is exactly the homotopy groups of this graph. But in a way, it's some weird homotopy theory that's supposed to measure like the maximal n-dimensional simplices in your complex, if that makes sense. So what Atkin was originally concerned with was he saw some people assigned to different committees at his university, that maybe some committees were becoming too powerful, or some people were becoming too powerful because of being on too many committees. Now, as someone who works at the department, I feel like no one is ever concerned. Like, we're concerned with people not doing enough work on committees, not people being too powerful on these committees. So to me, but the idea was that people were essentially the vertices of a complex, and then the simplices were the committees. So then the maximal simplices were the committees, right? And and then so he wanted to somehow model that and make sure that no one becomes too powerful. But essentially what you can do in order to reduce that to graphs is you take the maximal simplices as vertices, and then if they share a face of a specific codimension, you get you draw an edge between them. So that was Atkin's application, and that's how Barcelo, Kramer, Laubenbacher, and Weaver started. But then it turned into they realized that really it factors the graphs, and with graphs it's more easily expressed, and also it's easier to just find examples of graphs. Kind of like, we know that we can turn simplicial complexes into graphs, but also there are other things that we can maybe more naturally turn into graphs than simplicial complexes. So so that was the reasoning, I think. But maybe I should also say that, like, there are many different homotopy theories for graphs. So one thing that I made certain choices here. I made the choice of using the box product. I made the choice of using of taking graphs to have these loops. For instance, if you take the categorical product, the one with diagonals, but you don't necessarily, like, you say that the loops are optional, you're gonna get what's known as cross homotopy theory that is used in graph coloring. So that was developed by Dr. Mann and was applied by Babson and Kozlov to prove a conjecture of Laubenbacher. So that was one flavor that I presented. I think one that has most applications, but there are other flavors.